connect all of us at the same time. That is why I prefer the offline recordings that you can watch at your own time. Because now that you're working, each one has got a different schedule. So it's difficult to get everyone at once. But I felt that I wanted us to have this class specifically for the HEAT module. If you remember, we didn't finish module 1. We touched on I think just 3 topics. I'm going to keep it like that for the next test. I won't add more topics on module 1. Then we will do that. Then we will complete that module after this test. Because I know there's a lot to go through. I'm concerned about module 5. I must just find out whether the test is going to be 70 marks or 100 marks, because the test 1 was supposed to be 35, but they said we must make it 50 marks for the online learners. So I must just find out about the total marks for the second test, for this test that we're going to run. And then the other thing, just to make sure everyone is on the same page in terms of the modules that is going to cover. It's going to be the same topics on module 1, which we covered for the first one, for the first assignment, and then module 2, module 3, module 4, and module 5. So I wanted us to just go through module 5, because I feel there's quite a lot there that I want to take you through. So let me share my screen. Because you actually need to invest time for this module. But because it's if you've done engineering science N2, which I assume you have, it's a module. Can you see my screen? Just an indication?
Yes, ma'am.
Okay, thank you. So it's not completely new, but there are some add-ons here and there. So it covers these main 4 topics: the specific heat capacity and heat transfer, where you have the heat released by the warm substance and that heat is absorbed by the cooler substance. Then we have heat value of fuels, same as N2. Then we have expansion. The only difference with expansion is that in N1 and N2, we did linear expansion only, where we look at the increase in length. But with N3 now, we're going to look at area expansion as well, meaning the length and breadth. So that's the only difference. And also the steam we covered steam in N2. I would think all the theory that concerns the steam was covered in N2. It's only in N3 that we're going to do calculations for steam. Okay, so let's look at the specific heat transfer as a specific heat capacity and heat transfer. Okay, let me just see if I need to admit someone. Yes. Okay, so yeah, you need to be able to define what specific heat capacity is and indicate the units which it is expressed. So you will remember in N1, if you did N1, we covered specific heat capacity and heat capacity. Then from N2, we started looking at specific heat capacity only, which the only difference is that the specific heat capacity is specific to 1 kilogram, whereas the heat capacity looks at the whole content of the substance. And then briefly explain why the specific heat capacity of substance differ and what is the meaning of the specific heat capacity of a substance is. And some time back, they asked what are the reasons for what are the advantages and the disadvantages for the high specific heat capacity of water. That can be drawn from general knowledge if you know what specific heat capacity is. Just to mention it briefly to help your thinking, the specific heat capacity of water is so high. As an advantage, now we use water bottles, because if you have that hot water in that bottle, because the specific heat capacity of water is high, meaning that it absorbs a whole lot of heat energy to increase its temperature. So because that energy is a lot, it takes a while to release it. Hence, we put water in that water bottle, not any other liquid, because water is going to retain that temperature for a longer period. And also we use water for cooling because it can absorb large amounts of heat energy because of the high specific heat capacity. So just that discussion around what specific heat capacity is and what is the meaning when it's high or when it's low. And another example, because the specific heat capacity of water is high, we won't use the microwave to heat up water or to boil water specifically, because it's going to take a while. But if you put milk in a microwave, you're going to make sure that your settings are correct, because if not, before you know it, the whole thing bubbles up and you've got no milk, because the specific heat capacity of milk is so low. So just a little bit of heat energy is enough to raise its temperature. So look at that theory. And then when it comes to heat transfer, we look at the law of conservation of energy, which looks at the reality that heat energy will always flow from a region of high concentration of heat to a region of low concentration of heat. So that is will be now the conservation of heat energy, if it specifies that it's heat energy. And then 5.2.2 say indicate the way in which heat is transferred from one body to another by means of the law of conservation of energy. Apply the law of conservation of energy in calculations concerning mixtures consisting of not more than 3 substances. Now, when it comes to this, in N2, we looked at 2 substances. So you would have the hot body that is releasing heat energy, and then you would have the cool body that is absorbing that heat energy being released by the hot body. But now at N3, they might include 3 substances instead of 2. So maybe they would say hot steel bars are being put into water to cool them down. But this water is in a copper container. So now you've got the copper container plus the water that is going to receive the heat from the steel bars. So that formula would then be, let me make an example. You would say the heat released by the steel will be equal to the heat absorbed by the water plus the heat absorbed by the copper container. Okay, where you will use the specific heat capacity of water, the specific heat capacity of copper, and the specific heat capacity of steel. I believe you've been to your question paper, because your question paper gives this page as well, physical constants. Now at N2, this was just a little bit of information at the beginning of the question paper. Now at N3, it's a whole page. Have you come across this page? This is where you'll find your specific heat capacities. You've got one for steam, for water, for aluminium, for oil, for steel, and for copper. So those are the specific heat capacities. In your equation of Q is MC delta T. That fits in for C, C being the specific heat capacity on that equation. Q is MC delta T. Okay. So that will be the only difference when it comes to N3, that they might add the third substance, but one is releasing and the other 2 are absorbing. So those that are absorbing, you just add them together. Okay, so that is just your theory. You must know how to convert from degrees Celsius to Kelvins. It's not always necessary, but here and there, because normally if they give you the temperature in Kelvins, then the specific heat capacity is also in Kelvins. Then in such a case, there's no need to convert. And then just remember that for water, where will this be now? For water, 1 kilogram is equivalent to 1 liter. But this is for water only. In N1 and N2, we mostly used water. So we said 1 liter equals to 1 kilograms. That is only for water. But for other substances, if they give you that volume in liters, you're going to have to convert it to cubic meters first. then you can apply this formula. Mass is volume times density. You don't need to memorize this formula because where they have the constant information, they give you the constant value there for densities as well. Let me just go there. So you can go there to copy the formula. You see that is density of copper, aluminum, gold, alcohol, mercury. So they give the value and they give the SI units. So this means density is kilogram per cubic meter. So meaning density is density is mass over volume. But this volume must be in cubic meters. That is why I said now you need to know how to convert your liters to cubic meters. You must be able to convert your liters to cubic meters. If you forget that, you can Google that, but 1 liter is equivalent to 0.001 cubic meters, which means if you have liters, you will divide by 1,000 to get your cubic meters. So that is just one thing that is important to remember there, that it's only water where 1 liter equals to 1 kilogram. If it's oil, then if they give you liters, that is volume. Anyway, you need to multiply that volume by density to get the mass. And then I'm sure you've come across this, that the change in temperature is basically just the difference from your higher temperature to your lower temperature. So that is what we did in N2. The heat released equals to the heat absorbed, which I said just now. If there is a third substance, you will look at whether that substance is absorbing or releasing, and then you will add it on the appropriate side. Then when it comes to heat value of fuels, just keep in mind, heat value is also called calorific value. So they will use any of these terms. You must be able to define what heat value is. You must be able to do calculations on heat value of fuels, including the law of conservation of energy. Calculate the efficiency as well. Now, you need to know few examples of fuels, because first and foremost, you need to identify a fuel when it's given. So you need to be able to identify, if they say hydrogen, you need to identify that that is a fuel, because a fuel will have as a heat value, whereas a substance will have a specific heat capacity, so that you don't confuse those two. A fuel will have a heat value and the substance will have a specific heat capacity. So on this page, you've got heat values. This page is found on your question papers. You've got heat values for coal, for anthracite, for petrol, for hydrogen. And then you've got specific heat capacities as well. So you need to be able to identify which is which. And then the formula to calculate the heat energy of a fuel is mass times heat value of that fuel, and the one of a substance is MC delta T. Then you'd need to be able to solve problems in N3 whereby you have heat energy conserved, which means no heat losses. The heat availed by the fuel is the same as the heat received by the substance. On the other side, you also need to solve problems when you have some heat losses. Now, once you have heat losses, it means your efficiency is less than 100%. So your input heat energy will not be the same as your output heat energy. So your output heat energy will be a little less because of the losses. So I think we covered that in N2. I found that working with this framework helps a lot because your fuel is always the input in your system. Then it works through a machinery to deliver the results. So the results will be your output or your substance that was being heated up, or in a case of an engine, will be the performance of the engine. So your challenge here also, as they give you the information, is to be able to identify who's the output and who's the input. In a case of an engine, if they say the engine delivers this amount of power in watts or energy, what the engine delivers is the output of the whole system. But what the engine requires is then the input. If you can distinguish those two, then you can't go wrong. If they give you the fuel, then the fuel always falls in as the input. So the Q of the fuel is the Q in, and the Q of the substance is the Q out. So these Qs are representing heat energy. And in between, you have the efficiency bringing the two together. So efficiency is output over input. In this case, it's going to be the Q of the substance over the Q of the fuel multiplied by 100%. Just remember the percentage, you don't put it in your calculator, you bring it down as the SI unit. So you put in the 100, but not the percentage. So yeah, these are just examples. These are part of the notes that I've sent you. But I think I must just double check whether I've sent you these notes or just the old PDFs that I use, because you keep updating them as you go along. Then with expansion, we covered linear expansion in N1 and N2. And these are the equations that we worked with in N1 and N2 for expansion. We had the equation to calculate the final length, and we had the equation to calculate the change in length, just those two. Now we are adding area expansion. So we worked with these in N2, yeah, because in N1 we didn't do any calculation. So we worked with these in N2. Are we still okay? Are we still together? Just an indication. Okay, thank you. So we worked with these equations. So these equations are for linear expansion. Then the ones below are for area expansion. As you can see, they are similar. The only difference is that change in length becomes change in area. Original length becomes original area. The coefficient of linear expansion becomes the coefficient of area expansion. Now, the coefficient of linear expansion, you get it from this table. But on this table, you only have the coefficient of linear expansion. Here are your coefficients. Coefficient of linear expansion for copper, for aluminum, for steel, for lead. And then for area, to get the coefficient of area, you just get the one of linear and you multiply it by 2. So that value, so the coefficient of area is twice the coefficient of linear. So on the table, you only have the coefficient of linear expansion. Okay. And the key thing with expansion is to understand, because with linear expansion, you're going to end up with 3 lengths. It's going to be the original length and how much it increases by, and what is the total length while the temperatures are still in extreme, whether they are extremely high or extremely low. Same with the area. You've got your original area, and then you've got the area that it increases by, which is your change in area, and then you've got your final area while your temperatures are still in extreme, whether extremely cold or extremely low. Just remember your coefficient for area is twice the one for linear. So to get your coefficient, you just need to identify what material it is, and then go get the coefficient from the table. And then these are the equations I've put together. I got a feeling that the PDFs you have are not updated, so I must PDF this one and send you when we finish this class. So that's all you need. These are your equations. So as I have shown you already that they are actually similar. The only difference is that your area coefficient is twice your linear. So that's the value. Okay. So sometimes they give you the information, and then at the end, they say calculate the new dimensions. Now, if you want the new dimensions, it means you want the new length and the new breadth in a case of area expansion. In a case of linear expansion, you just want the new length when the temperatures are extreme. So this is just an example also. You haven't got enough time to just do all the examples. Yeah, I would encourage you work on that activity. Then if you have questions, you can WhatsApp me. And then when it comes to STEAM, we did all the theory in N2. Just want to download the STEAM tables. The only difference in N3 is that you're gonna need to work with you're gonna need to do the calculations. Okay, let me just make it big. So to do your calculations, you're mostly gonna use the STEAM tables. So how the STEAM tables work is that you've got columns. The first one is P, kPa, which is your pressure. Then you have your saturation temperature. Then you have your, we don't use VG. Then you've got your HF, HFG, and HG. So your HF is your liquid enthalpy, your HFG is your evaporation enthalpy, and your HG is your enthalpy of your dry steam. So the assumption is that you've covered your theory in N2. You know what these symbols are. So in N3, let me just go back to the notes. So this is the theory we covered in N2. We looked at important terms regarding steam, advantages of steam, applications of steam, and disadvantages of steam, phases of steam, phases or stages of enthalpy, the enthalpy versus the temperature versus enthalpy graph, solving problems. So here they give you some of the definitions which you've covered already in N2. That's your advantages, disadvantages, your phases of steam. You get wet steam, dry steam, and superheated steam. And this explains how you move on from water, boiling the water where it becomes vapor, heating that vapor further, and then it becomes dry steam, and then heating the dry steam further until it becomes superheated steam. So the superheated steam is the one that is ready for operation. So this was N2. So in N2, we learned that you start off with liquid. So you've got energy relevant for liquid, which is the liquid enthalpy. And then from the liquid enthalpy, when the liquid boils, it evaporates, you get evaporation enthalpy, HFG. And within the vapor, you have wet steam, which is H wet. And then when you take wet steam and heat it further, it becomes dry steam or dry saturated steam, which is HG. So on the table, you've got HF, you've got HFG, you've got HG, but not H wet. And then superheated enthalpy is HSU. That's also not on the table. Saturation temperature is on the table. Remember, the first column was pressure. So, but superheated temperature is not on the table. You've got saturation temperature. So saturation temperature is the temperature at which water boils and changes to steam. Okay, this is just further explanation. Additional terms and symbols, additional to those ones that you saw. So we saw the saturation temperature, we saw the superheated temperature. Then TV refers to the temperature of the feed water. Now imagine you've got this huge boiler plant that you are going to use to boil water to generate steam. Now, as you feed water into the plant, it's already at a certain temperature. So that TV refers to that temperature of the feed water as you feed them into your plant. And the specific heat capacity of steam, we use the symbol CP. Remember the specific heat capacity of just the other substances, we use C. But then for steam, we use CP because you need to differentiate, because in this case now you're going to have water as well as steam. So you're going to use the specific heat capacity of water as well as the specific heat capacity of steam. So these are basically the only equations that you're going to need. Remember, I said the H wet is not on the steam tables. The steam tables, you've got HF, you've got HFG. So X is the dryness fraction. Normally, they will give you the dryness fractions, 0.96, 0.98, whatever it is. So the dryness fraction tells you how much water is still contained in the wet steam, because wet steam is steam that still contains some water droplets in its suspension. That is why we are able to see when it evaporates, because steam in itself is clear. But we see wet steam, what we see there is not the steam, it's the water droplets that are contained in the steam. So they will give you the dryness fraction. So that's the formula to calculate the enthalpy of wet steam, HF plus X HFG. So what they will do, they will give you pressure. You take that pressure, you go to the steam tables. You go to the steam tables. My steam tables, where are you? Of things open here. It's a PDF. You go to the steam tables with the pressure. Now the pressure that's on the steam tables is already in kilopascals. If they give you pressure in pascals, convert it to kilopascals. If they give it to you in megapascals, convert it to to kilopascals. And then you use that pressure. So if the pressure, let me make an example. If the pressure that you are given is what? Is 500 kilopascals. Okay, let me use the first one so that I can still see the headings of these columns. Say the pressure is 70 kilopascals. So the liquid enthalpy HF is 377. The liquid, the enthalpy of vapor is 2283. And the liquid, the enthalpy of dry steam is 2660. So these are the SI units. It's energy. Enthalpy is energy that is contained in a unit quantity of matter. So it's kilojoules. It says here per kilogram because all the values that are on this table, they were derived using 1 kilogram of steam. But the SI unit for enthalpy is kilogram, is kilojoules. So this is all for 1 kilogram. Now, if the question talks about 2 kilograms, it means the value you have on the steam tables, you will multiply it by 2. If it says 5 kilograms, the value you get from the steam tables, you'll multiply by 5. Now, you'll either multiply the individual values, or you can calculate and get the final answer and multiply the final answer. It's going to bring you the same results. Yes, but when you write down your SI units for enthalpy, you don't write kilojoules per kilogram. You just write kilojoules because the kilo per kilogram only indicates that this whole thing was calibrated using 1 kilogram of steam. Yes, and then see what else is important. So that is the first formula, the formula for enthalpy of wet steam. So the question will say, calculate the enthalpy of wet steam or determine the enthalpy of wet steam. The one for dry steam, you do have a formula which you don't actually need. You might use the formula if you are given maybe one value and you're looking for other values, but in most cases you won't need this formula because Hg is given on the table as is. It's given on the table. And you will see it's similar to the one of wet steam. The only difference is that it does not have X because dry steam is now dry. X only indicates how much water it still contains. It indicates the mass of water contained in the steam. So that's why the formula for dry steam looks similar, but without the X. So you don't actually need this formula, but I put it on there because I think it's on the formula sheet and it's part of the notes. Let me just see. What equations do you have here for steam? Just to be sure. In fact, I think, yeah, you only have this one, which is for wet steam, HF plus X HFG. So the one for HG is HF plus HFG without the X. But like I said, you don't need it because you got HG on the table just directly. You only need to know either the pressure or the saturation temperature, and then you can get your HG directly from the table. Then the equation that you don't have on the formula sheet, which you need to remember, is the one to calculate the enthalpy of superheated steam. So that one is HF plus HFG. If you notice, this part is HG. This part, HF plus HFG, is actually HG. Okay, plus CP. So what is CP? It is now, I think I need to admit someone. Do I? Okay, myself in WhatsApp. So here you can just write Hg plus CTSU minus TS. If you notice this part, this is actually MC delta T. Yeah. Let me just write it down here so I can show it as I'm gonna show what I'm writing shortly. I just wanna copy it down plus CP into TSU minus TS. Okay. So what is happening here? So that's the formula you have. Superheated enthalpy is HF plus HFG plus CP. So this is the part that I'm saying, this is actually your MC delta T, that part. So this part is actually your enthalpy of dry steam, your Hg plus your MC delta T. But the M is omitted because the whole thing is for 1 kilogram. Remember, I said the values that you have on the steam tables, they are all derived looking at 1 kilogram. So this part here, that's your MC delta T. But because you're calculating for 1, then you omit the M, you have C times delta T. So your delta T is your superheated temperature minus your saturation temperature. And this side, this is your enthalpy of dry steam, which you can just get from the table using your pressure or your saturation temperature, whichever is needed. So if they want you to calculate the enthalpy of superheated steam, they will have to give you the temperature of the superheated steam, which we call TSU, the superheated temperature. And then that last part, minus CTV, that is the temperature or the MC delta T of the feed water. Remember, I said you feed the water into your plant. So again, M is omitted here because if you're calculating for 1 kilogram, then the whole thing is for 1 kilogram. If they say 2 kilograms, you can calculate, then at the end, you multiply it by 2. Then it's going to cover all of it. So just check, what is that message? Don't get frustrated. We're going to share this lesson. Don't get frustrated, please. Thank you. So this part, remember I said the C is now the specific capacity of water and the TV is the temperature of the feed water. So if it's included, I made it red because most of the time they say ignore the energy of the feed water. So if they say ignore, you cut that equation. You don't include that CP, that CT at the end. So this is just further explanation that you have in your notes that the first column is pressure, the second one is saturation temperature, then the liquid enthalpy, we don't use this one at N3, and then the evaporation enthalpy and the enthalpy of dry steam. And yeah, and that is all for the steam module. So as you can see, there's quite a lot of topics that are covered. So you need to make sure that you start as soon as you can, because we've got this week. Because then early next week, the assignment is coming in thick and fast. Any questions? You are all muted, so you're gonna have to unmute yourself to speak. Okay. Yeah, so this, as I said, the steam was my concern because of the length of the module and these little bit of differences that it has from N2. And then those of you that are doing mechano, hydraulics won't be a big deal for you because you do cover the hydraulic press there in hydraulics. And it only has 2 topics. I think it's in that week that I will add the other topics for module 1, just to do videos, the ones that we didn't cover. Yeah, by next week, I will do that. While you're busy focusing on the assignment, I will do the recording of those other topics in module 1. I think hydraulics is on YouTube already. And then I must just get to record electricity.
Sorry, ma'am.
Yes.
I just have a question regarding the first 3 modules then. Are we still gonna be covering the same topics in those 3 modules and then only adding these 2
Yes.
modules 4 and 5 for the next week?
Yes. Yes, we're gonna do it that way. So for module 1, it's the same topics that we covered in assignment 1, and then module 2, 3, 4, 5. Yes. So we're basically adding 2 modules, you're right, friction and heat. Yes. Okay, then if there's no other question, let me just check. Have you been able to access the Google Class? Have you tried to go there? Because I never posted the question papers on WhatsApp because they are too much. They are too much because they are here on the Google Class.
Hi, ma'am.
Yes, please come again.
Hi, ma'am. Listen, with regards to the student hub, there's certain modules that had to be filled in and gone through that fills your percentage and stuff like that. Is that still necessary?
No, 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 it's not. Because what counts here is your assignment 1 and assignment 2. And because
Okay,
of the
thank you very
challenges of logging in, so that is why Student Hub, we basically use it to send messages. We're not even encouraged to add videos on there because that company is working with all the colleges. So as Northlink College, we don't want to load our content on there because of that.
Okay, thank you, ma'am.
Yeah. So you're not missing anything if you're not able to connect on Student Hub. So here are the past question papers. Here, it's a whole long list of them. I've put in the question papers and their memorandums. So you should use this to practice. Okay, if there's no other questions, then we can conclude this class. So first thing tomorrow I will load this video on the student on the Google Class. I will load it on the Google Class. Yes.
The 8-week test, are we gonna write it the same as 4th week one?
Yes.
Like it's gonna be
Yes,
okay.
we're gonna write it the same way because they haven't got capacity to invigilate these tests. Remember, we are just tutors, but we've got our full-time work with the full-time students, so we're not available to go stand there and invigilate. So we will use the same procedure.
Okay, thank you.
But make sure you do understand your work. Even if you get someone to assist you with the assignments, make sure you do understand your work so that you can cope with that final exam. All right, then. Thank you. If you haven't got any other questions, you may leave. We can finish the class now. Thank you so much for making time.
Thank you, ma'am.
It's a pleasure.